This is a Federal News Network podcast.
Even if you're not a space geek, you may have heard of the moons Europa and Enceladus, both of which orbit Jupiter and Saturn respectively. They're famous for their potential ability to host the building blocks of life beyond Earth. Well, new research from NASA shows that those building blocks may not be that hard to find if we were ever to send a probe to do some digging around on those planets, on those moons. Alex Pavlov is a NASA space scientist who led this research, and he joins me now. Mr. Pavlov, thank you so much for taking the time.
Thank you for this opportunity.
Absolutely. So what can you tell me about this research? How did this all come about, and what exactly were you all looking for when this started out?
Well, as you stated, the Enceladus and Europa, they're airless bodies. And if you have airless body, then you have to be concerned about the radiation of the surface. So if we're taking samples from the surface of either Europa or Enceladus, we want to make sure that any type of potential biomolecules are not completely reworked by radiation. So our experimental study was essential to simulate effects of the ionizing radiations on these two icy moons and determine how long will it take if life is there, or if particular biomolecules will end up on the surface of those moons. How long will it take for them to completely be destroyed, or how long will it take to survive for a significant fraction of them? Because that will be very important for future missions to Enceladus and Europa, whenever they will be.
Okay, and so you were trying to figure out just how long those building blocks, and we should specify those are amino acids, a bunch of other good stuff that really started things off around here, and you wanted to see how long they could survive in the harsh environment that those planets' atmospheres create before they were destroyed. Are they buried underneath the ice? Because those are ice planets, right? Or ice moons, I guess. Right.
Yeah, so it's important to say these icy moons, they don't have really the atmosphere. That's why ionizing radiation is so concerning. Like on Earth, we are doubly protected from radiation because we have thick atmosphere and we have magnetic field. That's not the case there. So we have to pay attention to this. And we simulated, we took samples, the icy samples, we dissolved amino acids and dead microorganisms in those ices and exposing to gamma radiation, which is a proxy for ionizing radiation we expect on those moons. And then, calculated the dosage and see how long, or what dosage they still be recognizable, the significant fraction of this amino acids would be recognizable, which can tell us that, hey, originally there was life there, and it turned out to be that time take to destroy it. It's actually quite long. It takes, on Enceladus in particular, it takes, 100 million years to wipe it out, even very close to the surface. So that means that the ice on Enceladus would have a time to turn around, and will become a new ice before the amino acids can be destroyed. So that's why if a future lander, whenever that might be, will land on Enceladus, it will have a good chance to detect amino acids from the interior of the planet. And so if there is life, we will be able to see this. On Europa, the situation would be a little bit more. It's hotter because the radiation level is higher. There's no questions about it. But there are still spots on Europa in the high latitudes if you just dig by basically 20 centimeters, which is 10 inches or 15 inches, something like that. There's still that enough thickness to protect those molecules from complete destruction. So there are certainly locations in Europa where you still don't have to dig deep and still will be able to see biomolecules.
We're speaking with Alex Pavlov. He's a space scientist with NASA. So that's fascinating how resilient these amino acids and molecules are just from a little bit of protection from some of the ice. What is it about the ice that shields it from the radiation that is constantly being blasted at it from space?
Well, it's not as much ice as much as temperature helps. First of all, so the colder the temperature is better in terms of preservation, right? So if you break the molecules, they are not as subject to attacks by oxidative radicals, which radiation is producing because nothing is mobile in the ices at these temperatures. That's one fact. And the other one, as I mentioned, we didn't just look at the amino acids from dead microorganisms. So our logic was, right, let's just suppose the cells are there, right? Suppose life is in the ocean. It might incorporate as amino acids dissolved in water, but it might incorporate as a cell. right, is a chunk of organic matter. So in some of our samples, there was pieces of E. coli, for example, right, of dead E. coli. And we found out that amino acids in those chunks, in those organic chunks, they degrade much slower than individual amino acids, right? They are kind of, because of the organic matter is around them, again, oxidative radicals, which produced by radiation, have troubles to get to them, and that overall means that the amino acids, the biomolecules, the tracers of life will withstand for a longer period of time. So that's kind of what our findings were.
And just a curiosity question about how the research was conducted. You said you were able to calculate. You obviously didn't watch these for hundreds of millions of years. What goes into the calculations of determining, this much happened in a day, and you just kind of multiply that? Is it that simple, or is it a lot more complicated?
So we know the fluxes of ionizing radiation at the icy moons, right? They're partially they're model, partially they're observed. And we can calculate about the dosages, the dose rates, how radiation accumulation dosage per second, if you wish. And then we say, well, all right, the ice is about, up to 100 million years old. What would be the total cumulative dosage those ices would accumulate? Having this dosage in mind, we'll go to our radiation facilities here on Earth. And so obviously we will have to irradiate. We can't wait for 100 million years. We have to blast them out at a much faster rate, right? So we went to the nuclear reactor at Penn State, and we blasted it with gamma radiation there, to accumulate the total dosage. We did experiment over a couple months, but obviously, so it will be a much faster radiation rate, but the total dosage which they would receive there would be the same. And based on those dosages, we can calculate, so amino acid decays about at that rate. Different kinds, and if it's in E. coli, it decays slower, so that in mind, having this radiolysis constants, which is essentially efficiency, how they decaying, we can then extrapolate to what's happening on these icy moons and make, on the surface of Europa, not so well, but some location 20 centimeters deep, that's okay, and Enceladus looks like everything is peachy, so wherever you land, you can just go ahead, scratch the surface like a couple millimeters, and you're in business.
Yeah, Enceladus sounds lovely, which is interesting because you had always heard, it's always been about Europa from, just what I hear in passing from space coverage. But so, yeah, let's talk any future visits that the agency or anybody else really has in mind. You had mentioned that if we were to send a probe to either of those two spots and just, do some light digging, we could potentially find these amino acids and protein builders and things like that. What would be the significance of that? Obviously people think we discover life, we're looking for even microorganisms moving around, but just finding those building blocks, what would that significance mean for finding extraterrestrial life or even just the beginnings of it?
Well, obviously we relate it from our perspective, right? From our perspective, is all life as we know it is based on amino acids, and nucleic acids. So there's very few biomolecules which are present. And what we also know about amino acids, that they also chiral. They have, left-handedness, right-handedness. So all life favors the L amino acids, left-handed so-called amino acids. So, and when you'll find any amino acids in the universe and the meteorites, the abiotic amino acids, there is a little bit excess, but it's both left-handed and right-handed are present. So imagine if you landed on Enceladus or at the high latitudes of Europa, and after digging, you found out amino acids which are all right-handed or all left-handed. Based on life as we know it, that will certainly be very strong indicative that's life. That is not equal proportion of left-handed and right-handed. So that, no, it's not a cell per se, but, we do not know in nature the processes which will have 99% left-handed versus right-handed, so that's a tremendous motivation to go and dig below the ice eventually.
Well, until that point, what's the next idea that you got for testing out just how sustainable the environments on both those moons are? Obviously, you've thrown radiation at these molecules. What else are you going to do to make life tough for them?
To make life tough on them. It's in terms of all the chemical components, they are there on both icy moons. So the